third presenter is Joseph Real. Joseph Real was born in Putnam, Connecticut on July 26, 2008. He moved to Louisiana in April 2017 and went to Herndon Magnet Elementary Middle School. In 2023, he started going to Sea Bridge.
Atomos. This word, meaning indivisible in Greek, was first used to describe a particle so small you cannot make it any smaller. This idea, first introduced by Democritus in Greece around 400 BC, later evolved into the modern model of the atom. But how could you be certain of the existence of the atom? Well, physicists began to question this in the late 18th century, with Max Planck hypothesizing the existence of smaller particles than atoms. Physicists discovered the electron in 1897 and the proton and neutron in 1930 and 1932, respectively. Further on, however, the behaviors of atoms and their particles were the subject of the research that some physicists were carrying out. From then on, the age of quantum physics paved the way for advanced technology in the modern day. This all culminated into the modern quantum theory. Now, modern quantum theory, otherwise known as quantum mechanics, is a branch of physics that handles the behavior of atoms and subatomic particles. The basic principles of this field were built up over time, as most fields of mathematics and physics have been. Unlike the other fields of mathematics, however, quantum physics is fairly fast-paced considering how much it has grown in only a century. Where algebra and physics have been studied for thousands of years, quantum mechanics is a field that only appeared in the mid-1900s. Because of this, it is not a drastic assumption to say that quantum mechanics has been built with the cooperation of multiple different fields of mathematics and science. The statement is very much true. Also, unlike other branches of mathematics and physics, quantum mechanics is a lesser-known field of science. So before I go on to the origin of quantum mechanics, it is crucial to understand the basic ideas of this discipline. All right? I'm going to bring those to light here. Quantum mechanics, as previously mentioned, is a field of physics that deals with the behavior of atomic and subatomic particles. Now, physics deals with the behavior of larger bodies in space and time, so it would be easy to say that elementary physics focuses on the bigger picture, while quantum physics focuses on the smaller details. Unlike the larger world we live in, bodies and particles behave much differently compared to when they are isolated on the subatomic level. This is almost exactly like looking at particles with thermal energy, as we perceive them as having heat, while if you were to look at each individual particle, they are vibrating. In other words, these particles have kinetic energy, but when we look at them as an entire group, we say and label this as thermal energy. The entirety of quantum mechanics can be summarized as looking at past traditional physics to explain particle behavior using a different approach. In quantum mechanics, there are four main concepts that are used to explain particle properties and behaviors of particles. 1, particle-wave duality. 2, superposition. 3, entanglement. And 4, the uncertainty principle. Wave-particle duality explains how particles can behave as both waves and individual particles. For example, a photon of light is most commonly shown as a wave since photons act as waves. But a photon itself is a particle and it acts as one once its state is measured. Superposition is the fact that particles can retain multiple states at once. For example, the famous thought experiment of Schrodinger's cat best explains superposition, where a cat is put in a box with a device that has a random chance to kill it within 1 hour. And because of this, the cat is both in a state of death and life simultaneously until it is observed. Entanglement occurs when two different particles in separate systems are on the same state simultaneously, despite distance. This can also be explained with two different electrons sharing the same spin, even though they are a mile apart. Imagine flipping a coin in New York and in Paris and getting the same side in both cities each time you flip the coin. The uncertainty principle states that when measuring the state of a particle, it is not possible to know both the velocity and position of the said particle. This can mostly be attributed to the fact that particles, such as electrons, are constantly moving in a mostly random velocity and therefore cannot have their speed measured and their position measured in one moment at the same time. These main concepts, although somewhat simple in the context of the entire subject, are most important in quantum mechanics, although they are not the only ones. Another basic idea in quantum mechanics established by the physicist Max Planck is that the smallest amount of discrete energy packet that can make an observable change in a particle is known as quanta. This was in fact one of the first ideas in quantum mechanics and likely one of the easiest to understand considering it is simply a measurement. Now, to begin with the old quantum theory. Max Planck had been studying the kind of light that is released from heat, also known as infrared light, since it was not known why different gases glowed at different colors in discharge tubes, which are similar to neon signs if you did not know what those are. Thus, on October 19th of 1900, Planck established his paper on blackbody radiation, introducing the idea of quanta. Unfortunately, he was unsure of how the equation he presented in this paper was able to work. Like many others that ended up in similar situation, not knowing the importance of their discoveries. This was, however, the beginning of a new era in science. Only time could tell whether these discoveries would go unappreciated or not. After Planck established his paper, other physicists and scientists started to add on to the ideas presented. In 1905, for example, famous physicist and mathematician Albert Einstein theorized that the total energy of a light beam can be quantized or quantified. Einstein is not closely associated with quantum physics, however, because he had heavy criticism towards it, unfortunately. 5 years later, in 1911, one Arnold Sommerfeld, would research the connection between energy quantization for position and speed. During the same year of Sommerfeld's research, Ernest Rutherford discovered the atomic nucleus, opening a door for another physicist to reimagine quantizing energy when it came to nuclei. Niels Bohr had been working in Rutherford's laboratory at the same time. With the new discovery, Bohr had already established energy quantization postulates and applied them to the nucleus that they observed, which was the hydrogen nucleus. When he did this, everything from previous experiments with the discharge tubes could be easily explained. With every diatomic gas molecule that they had tested, different energy levels could be observed from different colors of light that were emitted when electricity was passed through them. This one application may have been the initial driving force for interest in the field of atomic physics, too. Fortunately for all sciences, though, the First World War kicked off, and with it, the hindrance of most progress was slowed to nearly a halt. All of these different discoveries made before the mid-1920s make up what we know as old quantum theory. In this field, many different rules were established for existing theories, and now the ones, even the new ones that were built up starting from Max Planck's paper and onward. Old quantum theory was somewhat unreliable, however, as there was no precise way to measure the different qualities of atoms and quantities of energies or positions in particles, or even the speed of individual particles. Eventually, though, this would all change with the turn of the second decade of the 1900s. The Great War had slowed down research in this field to a point of near halt. Some were not stopped by this, though, such as one William Wilson, who made more progress on the same issue that Sommerfeld had also continued to make progress on. Between the beginning of the war and the armistice that ended it in 1918, however, almost no research was conducted. With the end of World War I, though, came the rapid expansion of quantum physics-related research, which can likely be partially attributed to the Nobel Prize awarded to Planck for his theorization of quanta from 1900. Although he got his Nobel Prize in 1919 because in 1918 there was some paperwork he had to go through first. Quanta, as we established before, are now known as Planck's constant. I'm sure you have heard that somewhere. Because of this boom in quantum physics, however, there were more theories and more situations to look into. More and more was refined within the field until eventually, in the summer of 1925, three physicists would put their heads together to formulate a more cohesive theory of quantum mechanics that was more precise and could explain much more. Werner Heisenberg had been trying to find broader ways to make guesses and had stumbled upon the idea of making tables of quantities. He gathered numbers from different amounts of energy or speed or position and put them together in a table. When his research director, Max Born, had been shown this, he realized that what Heisenberg was trying to do was make mathematical matrices. With this information, Heisenberg was better able to formulate mathematical problems he was trying to carry out. Little did he know, though, this would end up being the beginning of new quantum theory. In the summer of 1925, the beginning of this new era happened, and with the collaboration of Heisenberg, Born, and one Pascual Jordan, a new cohesive theory was born, the new quantum theory. This also was known as modern quantum theory, but much more was to be discovered, applied, and postulated. Now, with this, we have discussed matrix mechanics, which is part of new quantum theory. However, there's one other theory, there's one other new quantum theory to discuss. With the true and very much anticipated birth of the more precise quantum theory, many wanted to begin researching even further into this new physics, attracting even more physicists into the already growing quantum sector. Accompanying this was swaths of new situations to explore. In particular, one man brought a strange new idea to this field. In 1923, Louis de Broglie brought a peculiar thought to the table. A particle of matter could behave like a wave. This idea was extended from Einstein's past proposal in 1905 that light could take on the properties of individual particles as well as waves. And the proposal was confirmed that same year. So Broglie figured that this could be, by proxy, true for matter as well. This theory would answer the questions posed by observations found in calculations regarding the motion of electrons orbiting nuclei. Einstein saw Broglie's paper on this idea and immediately brought attention to its importance to the bigger picture that was quantum physics. It was through Einstein's response that another physicist, Erwin Schrödinger, became infatuated with this. Schrödinger had been repulsed by matrix mechanics, and he hated it with a passion. It was because of this that Schrödinger began to look into wave-particle duality towards the end of 1925. In the next year, he proved that wave-particle duality was in fact true. He found this with wave functions, and in the process, found that these functions could only be related to the probability of physical events. The equation he had worked hard to create, aptly named the Schrödinger equation, angered him to the point of making him try to disprove it for the latter half of his career. In this equation, however, it is shown that particles are both a wave and a consolidated particle. He was not the only one that disliked this theory, as Heisenberg even spoke to his colleagues about how he thought it was nonsense. But, in the end, Schrödinger had created a new way of looking at quantum mechanics, leading to an explosion of new scientists and physicists and scholars, all gravitating towards unlocking the secrets of the atom. From here onward, there were many different advances of technology, and many of them even involved quantum mechanics. At the end of the 1900s, quantum mechanics and the new quantum theory have been adapted into many different technologies, from atomic bombs to particle accelerators. And in recent years, quantum mechanics have even been used for more in advancing technologies that are coming to be, like fusion power. In 2025 already, we have seen the application of quantum mechanics in, as stated, developing quantum fusion energy, and also in quantum computing. This is just the tip of the iceberg, as no one will truly know what the next day will hold for advancement. Quantum mechanics have advanced technology so far in such little time compared to other sciences. This field is a culmination of both mathematics and physics over the past century and stands as a testament to the power of human collaboration in science. From the smartest minds of the 1900s to the scholars of today, and even the commoner, the sector of physics has impacted life through its acceleration and advancement. That is why it is important to appreciate what has been accomplished over the years. Nevertheless, modern quantum theory, likely the youngest of new sciences, has become a wonderful spectacle to see from its humble beginnings as a question of how invisible light transmitted. Thank you.